I think we can get started. Hello, everyone, and welcome to the Civil Seminar. Today, it's my great pleasure to introduce Dr. Oya Mercan, who kindly agreed to give an invited talk for the Civil Seminar this term. So as a quick background, Dr. Mercan is an associate professor and Edwin Edward Hart Professor of Civil and Mineral Engineering at the University of Toronto. She has received her PhD in Civil Engineering from Lehigh University in 2007 and has been an assistant prof at the University of Alberta until 2010 before she moved to the University of Toronto. So Dr. Mercan's research interests are in developing and implementing real-time testing methods that couple computer simulation and physical testing with applications investigating the dynamic behavior of complex structures, vibration mitigation and structural control, modular steel structures, and wind loading under climate change. Dr. Mercan is also the founding director of the Center for Climate Science and Engineering, or CSE, at the University of Toronto. So with that said, please join me in welcoming Dr. Mercan. Thank you very much again. So whenever you're ready, Dr. Oya, thank you.
And thank you so much, Dr. Najafi, for the kind introduction. So I will today talk about real-time hybrid simulation. But before I do so, I can briefly introduce the main research areas that we work on at the University of Toronto. So currently, I have a group of students who are looking at modular construction. You might have heard about it. It is a relatively recent method of construction, unlike the traditional structures, steel structures, which are built on site. These modular structures are prepared at a factory. You can think about these 3D volumetric units as a room, and they are fully finished. In some cases, they even introduce the furniture in it, and then they are shipped to the site, and they are corner connected. Although there is quite a bit of a difference in the detailing of these structures in comparison to traditional design, and the Canadian design codes currently do not have any specific information about the design of these modular structures, and my group is looking into understanding the behavior, dynamic behavior of these structures and different connectors for modular steel structures. Another area that is active in my group is related to the center that we have at University of Toronto Center. And in this center, we have an interdisciplinary group of faculty. And for this particular project, we are working with our colleagues from climate science to understand the wind loading effects in the future at the end of century or 2050. And we are following the Devonport wind load chain to do so. And what we do is, instead of using historic climate data, we are working with climate scientists to get the downscale data from future projections. And then the rest is the typical introduction of the wind load change to account for the influence of terrain, to account for the aerodynamic effects using computational fluid dynamics, the dynamic effects, and establishing the criteria as usual. The real-time hybrid simulation and motivations comes from seismic hazard mitigation. Here is an example of a seismic protective system, Torre Mayor office building in Mexico City. These large dampers dissipate energy during an earthquake and mitigate the vibration of the structural and non-structural components. To enable widespread use of these devices, we need to perform large-scale tests, real-time tests, and understand the behavior, the performance of structures equipped with such devices. And in that endeavor, real-time hybrid simulation is a very important tool. And if we look at the history of it, in 1960s, it actually started as pseudotime dynamic testing method, where we have the entire structure built in the lab, and we have loading components, hydraulic actuators to apply the loads. And typically, we discretize the dynamic systems as discrete parameter systems. We keep the analytical components for the inertial and damping terms. The external load is specified when the instant that you know the earthquake load, you can calculate the effective load. The restoring force characteristic, which is the harder part, especially if you have nonlinearity involved, that is experimentally obtained. So we have a numerical integration algorithm that solves the equation of motion. At each time step, it calculates the displacement of each floor. We have hydraulic actuators, they push the structure, and then using the load cells, we measure the restoring force from the deformed structure. So with this way, we don't need to model the structure. Any uncertainty related to the modeling of the structure, stiffness, strength, behavior is eliminated from the problem. So this gives us the dynamic response of the structure using an expanded time scale test. Hence the name is pseudodynamic. So typically these tests are done quasi-statically because the time-dependent components, velocity and acceleration-dependent components, are handled in the analytical substructure. In the hybrid simulation, the idea is similar, but instead of, for example, testing the 4-story structure with 4 actuators and realizing that typically the first floor is where the nonlinearity is concentrated, and second, third, fourth floors may be remaining linear and much easier to model. So we split the structure into 2. Part of it is called analytical substructure. We model it in a computer. Part of it is the experimental substructure. We test it in the laboratory. If you look at the flow chart, we start with the external load. The integration algorithm calculates the displacement vector, and now it splits into analytical and experimental. Part of the displacements are sent to the numerical model to calculate the restoring force. Part of the displacements are sent to an actuator to impose it on an experimental substructure. And once this step is done, the restoring forces, both from the analytical substructure and the physical substructure, are combined and fed back. This way, by only testing a critical component, we obtain the dynamic performance of the entire structure. And when it is hybrid simulation, it can be done on an expanded time scale. So real-time hybrid simulation is the latest version of it. And why is it real-time? It is important to capture the load rate dependent vibration characteristics. If your structure has a damper, an isolator, anything that has load rate dependent, and if you are doing hybrid simulation, you need to make sure that that experimental substructure experiences realistic loading rates. And for that reason, you need to do it either in a fast format, fast hybrid simulation, or in most cases, real-time hybrid simulation. So if you have an earthquake that is 45 seconds long, your hybrid simulation should start and finish within 45 seconds. And this comes with additional challenges. Here we are looking at the block diagram of real-time hybrid simulation. We have 2 loops. In the outer loop, we have the integration algorithm. It calculates the displacement. It sends it to the numerical substructure and the experimental substructure, which sits in the inner loop. In the inner loop, we have a controller that controls the servohydraulic actuator and imposes the displacements in real time to the test structure, which can be the first floor of your structure, as we have seen before, or a damper, an isolator, whatever you have substructured from your whole structure. And then the measured restoring forces are fed back, computed restoring forces are fed back, and the integration algorithm issues the new displacements. Inherently, the dynamic test method, hybrid test method, real-time hybrid simulation test method, they are prone to error propagation. So if we have error coming back from the computed restoring force or measured restoring force, it's going to distort the next step displacement. And with that, we need to be careful about the these type of error sources. So we started with identifying these error sources and looking at them in detail to understand how they work. So we separated the error coming back from the either analytical substructure or experimental substructure, it doesn't matter. We classified them as amplitude errors in the form of undershoot or overshoot, time errors, phase error, you can call them, in the form of lead or lag error. And when we looked at in detail to these 4 types of errors, what we found is that the time lag error is the most critical one. It has an equivalent effect of a decrease in damping ratio, and it can lead into instability of the overall outer loop dynamics. So when we look back to this block diagram, if we have tau 1 second of delay coming from the analytical substructure, another delay of tau 2 seconds coming from the experimental substructure, for some combination of tau 1 and tau 2, the outer loop dynamics can become unstable, so you can't even continue the test. And this is the worst case scenario, and instability during dynamic simulation is the last thing that we would like to observe in the lab. And in the best case scenario, you will have accuracy issues. So we started looking into this limitation by clearly understanding how the delay works in the outer loop. So we came up with this plate-dependent stability analysis for the outer loop system dynamics. As I mentioned before, in the outer loop, we are solving a differential equation. Inertial term is analytical, damping term is analytical, external force is numerically specified. We have some measured force, which may have a constant delay of tau seconds. We can take this second order differential equation and recast it what is known as state variable form in terms of first order differential equations in the matrix vector form. And if we look at in this form, we have the state vector x, state derivative vector x dot, delayed state vector xt minus tau, and delayed state derivative vector x dot t minus tau, and the A matrices in front are all coefficient matrices, that there are some numbers. So if you wanted to understand the stability of this system, we can look at the characteristic equation in state variable form in Laplace domain. Essentially, if I take this determinant and evaluate the roots of this characteristic equation, I can determine whether or not my dynamic system is stable. If we think about the delay term, if I don't have any delay, if tau is equal to 0, then this exponential term is 1. This determinant becomes a standard polynomial. And then I can easily establish the roots and look at the stability in complex plane. So if I have roots of my dynamic system on the left-hand plane, my system is stable. If I have roots on the right-hand side plane, I will have exponential growth in time domain, which means that my system is unstable, which makes the imaginary axis the boundary for stability. When we have 0 delay in our dynamic system, it's very easy to establish the stability. The problem comes when we have non-zero value of tau. When we have non-zero value of tau, that exponential term can be written in this infinite series expansion, and it brings infinitely many roots, making it very challenging to identify stability in this fashion. If you look at the literature, the first thing that has been done is to employ linearization, which means that the higher order terms of the series expansion is cut off. And obviously, this would not be valid for large values of tau. It is valid as long as you have very small time delay. But when you have large time delay values, this approximation will start to suffer. So what we did is we employed a pseudo delay technique, which has a substitution called Riccatius substitution. For this exponential term, we have this ratio of the 2 polynomials, and you see on the left-hand side, it is a function of tau. On the right-hand side, we have a new variable t, and there is a mapping relationship between tau and t, and you can show that this relationship is exact on the imaginary axis, with this mapping relationship. So it is only exact on the imaginary axis, which is the boundary for stability for us. It is not exact in the whole complex plane, but so long as it is exact on the imaginary axis, it gives us a very accurate description of the delay term. So what we did was, using the recursive substitution, we turned our characteristic equation, which was a function of exponential term, into a standard polynomial in S and T. We can study the roots for Q for stability, and when we find the value of T that destabilizes Q, we can then use this mapping relationship to quantify the corresponding time delay. And with that, we have published 2 papers that shows the stability analysis for real-time hybrid simulation when we have only single source of delay for STOF systems. And then we extended this to also capture multiple sources of delay for the application of multiple degree of freedom systems. This brings us to the tracking evaluation problem. Now that we have an idea to quantify when someone gives us a dynamic system, and we can quantify, okay, for this much delay, your system can be stable or unstable. So we have a tool with this delay dependent stability analysis to quantify that. The next question is, what is the delay that is coming from my experimental substructure? This delay comes from the inherent response characteristics of a hydraulic actuator. You want the actuator to move 3 millimeters in a millisecond, but it doesn't directly move. It is a physical system. It has inherent latency. So we spent a little bit of time in the beginning to understand the tracking performance. Once we realized that it is quite a complicated issue, we kept working on it, and we ended up having 3 different sets of tracking indicators. So here we are looking at the command and measured displacement comparison or 30-second duration from a real-time hybrid simulation. This is an actual real-time hybrid simulation test result. And when we look at this scale, it looks like we have a very good tracking between command and measured signal. But when we select a few time windows and look at it in the zoom version, we can see that in some instances, we have the measured displacement lagging behind or leading. So in order to quantify this performance, we came up with a synchronization subspace plot-based tracking indicator, an amplitude indicator. The idea comes from signal processing tools. A synchronization subspace plot is used in signal processing. It has the actual or measured response plotted against the desired response. So on the left here, we are looking at one cycle of sinusoidal signal. So the purple one is our command signal, and the green one is a signal which is measured and it has undershoot error. It doesn't arrive at the same amplitude as the command signal. And on the other side, the red one is overshooting. If we take these signals and construct the corresponding synchronization subspace plot, where the measured signal is on the horizontal axis and command signal on the vertical axis, if we have perfect tracking, if the command signal is equal to the measured signal, we would have the purple line. It is 45-degree inclination, perfect control, perfect tracking. But when we look at the undershoot and overshoot error, the undershoot error gives us an inclination greater than 45. Overshoot error gives us an inclination less than 45 degrees. Similarly, in here, we have the same purple command displacement, but this time instead of amplitude error, we are introducing lead and lag errors. So the on top of that, the amount of lag is bigger than the amount of leads. So the green line is leading, the red line is lagging, and they have different amount of phase introduced. And we are when we look at the corresponding synchronization subspace plot, this time what we observe is that when we have this type of lead or lag error, we no longer have straight lines in the synchronization subspace plots, but we have elliptical hysteresis. With the lag error, the synchronization subspace plots they evolve clockwise. With the lead error, they evolve counterclockwise, and the more phase error you have, the fatter are these ellipses. So with that, we developed tracking and amplitude indicators based on the areas enclosed in the synchronization subspace plots. But we realized that those indicators were affected by the overall amplitude of the displacements. So they were useful in comparing the real-time hybrid simulation test results between displacement time histories that have comparable amplitudes, but they were not perfectly uncoupling the phase error from amplitude error. With that, we went back to the synchronization subspace plot. This time, instead of using the area enclosed, we developed closed form expressions. If we fit an ellipse to the synchronization subspace plot as it evolves in this synchronization subspace, we have this equation for the ellipse. We derived amplitude and phase error definitions as a function of the coefficient of the ellipse. And we used image processing techniques, direct square fitting approach, to fit an ellipse as the experimental data populates the synchronization subspace plot. Once we have these coefficients through this direct square fitting, we used our closed form expressions to quantify the amplitude and phase errors. And these were capable of uncoupling the phase error and amplitude error. And they were also not dependent on the overall amplitude of the displacement. So you can compare two different sets of real-time hybrid simulation results independent of the amplitude of the displacements that are involved in those tests. However, they were, especially this stage of image processing to fit this ellipse involving a very large eigenvalue problem, it was not possible to implement this set of indicators as an online tool to see how the test is progressing as we are performing the real-time hybrid simulation, simply because the eigenvalue problem takes very long to implement and execute in real time. So we developed these indicators, and we use them as indicators that could be used as a post-processing tool. And later, we went back to this problem, and we used frequency-based approach. So we developed amplitude and phase indicators using fast Fourier transform, which I'll show in a couple slides later. These were as accurate as the phase and amplitude error indices that I introduced here. On top of that, they were computationally very efficient. So we were able to implement the last set of indicators online in real time, and we even used it to develop a form of adaptive control technique, which I'll discuss in a few slides. And this is an implementation of real-time hybrid simulation that we carried out at the University of Toronto. We took a Quanzer educational shake table. We introduced the necessary hardware and software to turn this educational shake table into a real-time hybrid simulation platform. And then we used it for research to understand the tune liquid damper structure interaction or the accuracy of the tune liquid damper models. So for the hardware, we had the shake table, and it had its own controller and data acquisition system. We had to introduce some sensors. And on the software side, the shaker came with its own controller. So the inner loop was kind of there. We introduced the outer loop, the integration algorithm and analytical substructure, and we used WinCon to coordinate, to synchronize the outer loop with the inner loop. And we also introduced some compensators to improve the controller, because in real-time hybrid simulation, accurate tracking of the command signals are very important for the accuracy and stability of the overall test result. So we published the implementation and verification as a journal paper, so that other institutions that have a similar shake table can use real-time hybrid simulation. And then we assess the accuracy of different TLD models by running quite a bit of tune liquid damper tests with this setup. We also were able to perform a large parametric study to understand the important influential parameters for TLD structure interaction. And a similar study would have been quite difficult to do on a shake table, because in this platform, we isolate the tune liquid damper. We only test the tune liquid damper, and we put the structure on a computer. So it doesn't cost us anything to change the parameters of the structure itself. But if we were doing this as a pure shake table test, we have to build a model of the structure and put the tank on top of it. So each time we have to change some parameters, we have to build a different structural model, which becomes costly and difficult. And we even design and investigated different TLDs with different base connectors. In this one, it has a pivot at the base. So when the structure moves back and forth, this tank does not only sway back and forth, but it will also rotate, increasing the efficiency of the TLD. And another real-time hybrid simulation platform that we developed at the University of Toronto is using hydraulic actuators and a generic national instrument controller. So we purchased a real-time PXI controller from National Instruments. It has field programmable gate arrays. You can think of them as programmable chips. And we have also developed our own custom data acquisition system. And this was a quite big endeavor to develop this system from scratch, because usually when you purchase an actuator, you would also purchase the relevant controller from the same vendor. If it is an MTS actuator, you can buy a FlexText controller. If it is a Shore Western actuator, you can buy a controller from Shore Western. So you wouldn't worry about how to control the actuator. But in our case, we only bought the actuators. We developed the controller from scratch ourselves. So we separated all the tasks into two. We programmed some of them on the PXI side, and some of the tasks on the FPGA side. And we synchronize them in LabVIEW direct memory access option. And I will briefly discuss the implementation of the software also. So we use LabVIEW together with Simulink. This is the front panel. It is the graphical user interface. You can set your sensor gains, you can set your PID gains, and then start running the real-time hybrid simulation. This is the front panel. But at the background, we used a state machine technique. We separated all the tasks into these small boxes, and we programmed them individually. And all of these implementations were done as a separate LabVIEW VI, a LabVIEW code. And then we modeled the structure in Simulink. So the host VI coordinates everything. It has the graphical user interface. We have LabVIEW, the state machine implementation that I just showed you. And then we have the structure that is built as a Simulink model that sits in MATLAB Simulink, and using simulation interface toolkit, by turning the Simulink model into a dynamic link library, we run it from within LabVIEW in real time. And that is how we developed this first user reconfigurable platform. And in the process, we had some challenges because National Instrument products are not built to control servo-hydraulic systems. For example, in order to drive a servo-hydraulic actuator, you need to issue plus minus 40 milliamp currents. but from national instrument controllers, you can only issue plus minus 10 volts, depending on your controller. And for that reason, for example, we have to employ voltage to current converters, and we have also some AC-DC conversion issues. So we introduce all the necessary adapters, and then all of these adapters require their own power supply. So we essentially ended up building a custom data acquisition system for this user reconfigurable platform to work. And although this was a significant undertaking, it was a totally transparent and flexible system. Now, whenever we develop a new algorithm, we can have complete access to the controller and the integration algorithm analytical substructure side, so we can implement it so long as we can program it in LabVIEW and we have enough computational power to execute the resulting code in real time. We are able to run real-time hybrid simulation to experimentally validate different algorithms. And we have used this to develop several different adaptive controllers for servo-hydraulic systems. And I can briefly go over a few of them. So the very first one is based on the frequency domain-based indicators that I described earlier. The idea is quite simple. In the inner loop, we have our constant coefficient controller, the system that we need to control. We have the command displacement and measured displacement. So we take these two, we introduce our frequency domain-based online indicators. They quantify the phase error and amplitude error between these two signals. We then design a compensator to negate these effects and put it to the forward path. So here is the LabVIEW implementation of this. So we have the adaptive controller with PID. We have the PID in the previous case. We have the PID constant coefficient controller. So what we do is we take the measured signal. We take the command signal. We perform fast Fourier transform, and then we have the our algorithm that calculates the amplitude and phase errors using this frequency domain-based indicator approach. We then calculate the coefficients of the compensator that needs to be introduced in the forward path to negate these effects, and then we build the compensator's transfer function and put it in the forward path. And here is a video that compares a constant coefficient PID controller, which is on top, with our adaptive controller at the bottom. So in both cases, the dashed blue line is the command displacement. And in both cases, the command displacement is what we call a chirp signal. It is a sinusoid signal that has increasing frequency. So as we continue with the simulation, the sinusoidal signal gets faster and faster. And as we can see here, although initially the constant coefficient controller does quite well, as the input gets faster and faster, it has a certain bandwidth. So it is not able to keep up with the fast input, whereas our adaptive controller at the bottom, after it finishes the adaptation procedure, it does much better for the faster end of the chirp signal. So after we have developed and experimentally verified this adaptive controller, we realized that it does a quite good job if it has only a dominant frequency at a given time window. So it can have multiple frequencies so long as they are one after the other. It does a quite good job in tracking it. Due to the way that we develop the indicators, where we have to select one dominant frequency, it does a very good job when you have a single dominant frequency in your time window that you are interested at that time instant. But when you have multiple frequencies that exist, it starts, the accuracy of the tracking starts to suffer. So here we are looking at the same adaptive controller. We have the adaptive phase beat compensator and the structure system. In order to handle this situation where we have multiple frequencies, we ended up introducing a supplementary PID controller to further remove this error, and we published it as a separate paper, which I'll show in the next slide. And another adaptive controller that we very recently verified is based on the model-based feed-forward controller technique. So here we are looking at the inner loop, which has this transfer function that represents the dynamic of the controller and the servo-hydraulic structure test structure system. So if we can identify the dynamic of the system accurately as a transfer function, and if we can somehow invert that transfer function and put it in front, you can see mathematically there's going to be perfect cancellation, which means that U is going to become X, perfect control. So in theory, this looks very promising, but in the implementation there are challenges. In the sense that you have to do a very accurate system identification to be able to get a transfer function that defines this dynamics, and then you need to invert it, and in some cases there is even problems in this inversion. But if you have a nonlinear component, you depending on the input you may have each time you do the system identification, you have a system with slightly different parameters and things like that. Or in some cases, you may have a very fragile test system, and it may be even dangerous to do the system identification with a broad range of frequencies and amplitudes, because you don't want to break your test specimen before even you get a chance to test it. So what we did was we introduced a discrete domain representation of this relationship between U and UFF, and also another relationship between UFF and X in this discrete domain representation, and the coefficients are adjusted such that perfect cancellation can occur. Instead of doing this system identification ahead of time, we introduced online identification to calculate the coefficients of CI by using UFF and X as we perform the test. And this way, the feed-forward controller becomes an adaptive controller. It is not a controller that has been defined with fixed coefficients based on a system identification that has done before. So if you look at this comparison between model-based feed-forward feedback controller, which was proposed by Phillips and Spencer from UIUC in 2013, they have the PID controller servo-hydraulic system inner loop, and their feed-forward controller is based on a system identification, hence the name model-based. In our adaptive discrete feed-forward controller, we take the signals to introduce a least square estimation for the online identification of the feed-forward controller, and then we use that to introduce the feed-forward adaptive feed-forward controller to improve the tracking performance of the hydraulic actuator. And we were able to, with our flexible user reconfigurable platform, we were able to implement this and experimentally validate it quite easily. And the last improvement that I want to show you is about the integration algorithm. Typically, the integration algorithm is kept as if you are talking about a single degree of freedom system, it is a single second-order differential equation. If you are talking about a multi-degree of freedom system, it is a set of second-order differential equations. But instead of using a set of second-order differential equations, in this case, we use state space formulation to cast it in continuous state space equation, and we discretized it using Euler and Runge-Kutta algorithms, and we have introduced some estimators and correctors to make it real-time adaptable, and using our national instruments PXI system as well as a disk space board to show that this works in multiple platforms. We validated it in 2 different platforms, and we published it back in 2016. So once we have developed and continually improved this platform, we also used it to understand the dynamic behavior of systems equipped with different supplemental devices. And in some cases, we developed some of those devices ourselves, and in some cases, they were existing devices. We tested them. So if you look at this table, these are some selected applications. The first four are passive control devices. So this is a gyro mass damper. One of my PhD students developed it. It works like a tuned mass damper, but you don't actually have the physical mass present. It has a gear assembly that amplifies the rotational inertia. And by transferring rotational and translational inertia to each other, you can generate translational inertial forces by introducing quite small physical mass. So that is the advantage of the gyro mass damper, and we were able to test it using real-time simulation. These are tuned liquid dampers. A small scale version of it was tested by using the Quanzer shake table real-time hybrid simulator that we developed and I showed earlier. These are the large scale ones. This one is a multiple tuned liquid damper. It has 5 compartments. The idea is to tune the water level in the largest compartment, the blue one, to the first mode of vibration, the side ones to the second mode of vibration, and the back ones to the third mode of vibration. And we were able to show experimentally that it is possible to control multiple mode of vibration using this type of TLDs. This tuned liquid damper is annular TLD, specifically for controlling the vibrations of wind turbine towers, and the geometry is designed to fit to that structure. This is a viscoelastic plastic damper. In collaboration with Professor Christopoulos, we tested around 200 real-time hybrid simulation we performed to be able to validate a design method called P-spectra. Professor Christopoulos' student developed it specifically for nonlinear supplemental devices. So we used real-time hybrid simulation to validate the design procedure. These two are active control devices. This one is an active screw jack. It works like the gyro mass damper. There is a worm gear inside this screw jack. When you introduce a torque to the handle, the piston pushes in and out. So we introduced a DC motor to control that torque, and we turned this screw jack into an active system and performed real-time hybrid simulation to show the improvement that we received by using such an active device. And the last one is the one that I want to show you in the next slide. This is called a deployable autonomous control system, or DAX in short. This was a study done in collaboration with University of Waterloo, and it showcased the use of robotics for the first time to enhance structural control. And the idea is to provide a temporary vibration control measure for lightweight bridges. And if you look at the DAX prototype, it is composed of an unmanned ground vehicle, this yellow car. It has its own robotic control system, and it has vision sensors at the back and front. And on top of it, there is an active mass damper, electromagnetic mass damper, which introduces the control force. And the idea is when we have a lightweight footbridge, pedestrian bridge that is vibrating, we can deploy one of these devices. It can sense the mode of vibration. It can calculate the optimum location with using its sensor and robotic platform. It can go to the optimal location and then activate the active mass damper to introduce optimal control force to control the vibration. And what we did in collaboration with the University of Waterloo is to use real-time hybrid simulation to experimentally validate this control system. So in this case, we have the analytical substructure composed of the bridge itself and the loading. And the experimental substructure is one of these DAX prototypes tested on a shake table. And the idea is quite similar as the regular implementation of the real-time hybrid simulation, but there are some very important differences. When we are using real-time hybrid simulation in building applications, the external load has fixed locations. So we know the load history, if it is from wind or from earthquake, we know the entire history before the real-time hybrid simulation starts, and we know the location of the application of that force. It doesn't change. Here, as the person moves or the people move, the loading changes. There is mobility of the load that needs to be accounted for in the real-time hybrid simulation. On top of that, in building applications, when we introduce the damper at some floors, or when we introduce the tune liquid damper at the roof, or tune mass damper, or the isolator, the location is fixed. The same mobility issue is here for the control device also. So we had to rethink how we introduce this analytical substructure to be able to capture these two. As on top of that, there was some dynamic interaction between the shake table and the data, because the DAX system. So we had to account for that also. And we published this collaborative work in 2019. And this finishes my presentation today. I would like to thank all the sponsors, all my collaborators over the years, and most importantly, I would like to thank my students and other researchers who have visited my group over the years to do the work that I presented today. And I thank you for your attention, and I would be happy to take any questions you may have.
Thank you very much, Dr. Mercan, for your very interesting presentation. You may all ask questions either using the chat window or unmute yourself and use the speaker, please. Dr. Ashraf, do you have any questions?
Yeah, thank you very much, Oya, for a very nice presentation.
Thank you.
I think the research on real-time and control is really fascinating. I want to ask you something, a general question. I see a lot of application this from research and development, but do you see applications in engineering, in practice engineering about real-time?
So this is a test method to be able to understand the global dynamic response of structural systems, and depending on the interest of the real application problem or the people who are involved in that, there could be very interesting applications also. But one of the limitations is that even in the most advanced laboratories around the world, you have a limited number of actuators. So this kind of determines the number of experimental substructures you can simultaneously test. So so long as those limitations are respected, even the current states that we have, the real-time hybrid simulation with the continuous development over the last 2 decades, I think this could be used to answer questions from real applications also. But for example, if you have a 40-story structure and you are using, I'm making up like 120 dampers, you cannot possibly test 120 dampers when you isolate them. You don't have that many actuators, and the geographically distributed version of real-time hybrid simulation. Hybrid simulation is possible, but real-time aspects cannot be successfully done across different laboratories. So depending on the problem, it needs to be evaluated. If the real-time requirements can be lifted, it could be done as geographically distributed. But if it is going to be at a single laboratory, then we have to work with the number of actuators and the available resources to address the problem.
Okay. Thank you very much.
You're welcome.
Any questions from the audience? Okay. They are quiet today. Maybe they are in the.
there are some
question from a student, I think. Interesting presentation, amazing work. Is it more economical to use hybrid simulation compared to direct shake tests?
That is very true. So and that is the motivation about behind the real-time hybrid simulation development. So it is much more economical and practical compared to shake table tests. For example, to our knowledge, this tuned liquid damper is the largest tuned liquid damper that has been tested in conjunction with a structure. Because we, for example, in these tests, we had 9-story shear building that has been used as an analytical substructure. So if we had to do it as a pure shake table, we had to build a scaled down version of a 9-story structure and put these tanks on top of them, which most likely would end up, because of the payload limitation and the also ceiling height limitation of the laboratory, the tanks that we would end up testing would be much smaller. And so with real-time hybrid simulation, we are able to use all our actuating power to test the component, the critical component, and we are modeling the rest. And as a result of which, we have an economical situation in comparison to pure shake table test.
Thank you very much.
I have another quick question. I guess the application of hybrid in testing under wind loads is probably easier than earthquake because of its longer period, or there is no difference.
The focus and majority of the work on real-time hybrid simulation was motivated for seismic applications for a long time. So yeah. Only recently, when the multi-hazard considerations became more important, the researchers active in real-time hybrid simulation started using wind loading. Essentially, so long as you quantify the wind load accurately, the introduced wind load history is representative. There is no major difference in the application of the real-time hybrid simulation. You are simply replacing the earthquake time history with wind load time history. So, but the duration and the frequency content, those need to be evaluated case by case basis.
Okay. Very good.
There's another question from Yi. When I took the structural dynamic course, the damping ratio is hard to be calculated, so many assumptions have to be made. Do you have any conclusions of the damping ratio from testing?
So this is okay. So in these hybrid simulations, usually the supplementary device, for example, if we pick this elastomeric damper, there is quite a bit of damping that occurs in this device due to the deformation of the elastomeric layer, or there is a friction fuse, and the combined hysteresis curve shows us there is quite a bit of energy dissipation. And now that we have this experimental data, we can estimate the overall damping ratio much more accurately. And this is valid for other types of supplementary devices. For all of these devices, we have displacement history and force history measured from the device itself, and that enables us to accurately quantify the damping characteristics. But the analytical substructure that we model, for example, in this case, I mentioned we are modeling a 9-story structure. We still make the inherent damping assumption as usual if it is 2% or 5% concrete or steel. So those are still there, and that the identification of the inherent damping is more of a structural health monitoring type of work. So we don't really get information from this type of test to be able to identify the inherent damping of the structure, because we start the testing by modeling that and making some assumptions. But for the components that we are testing, we would get accurate damping estimates because we have the experimental data from them. I hope it answered the question.
Thank you very much. Okay, thank you very much, Dr. Oya. Much appreciated. Thank you for taking the time. I know it's a busy time with teaching courses and all the research you do. We appreciate that, and we hope that soon you would come to London and give another talk, hopefully in person soon.
Thank you very much for the invitation. I really appreciate it, and I hope to see you in person also soon. Thank you.
Yeah, thank you, Oya.
Great.
Next time in person for sure. Yeah.
Great, thank you. Thank you, everybody, and see you next week. Have a great day.
Bye.